Welcome back, future engineers. I'm your professor, and today, in this explainer session, we are going to completely transform Kirchhoff's current law. We're taking it from a dry mathematical formula on a page and turning it into a highly intuitive, incredibly powerful engineering tool for your circuit analysis class. All right, let's dive right into this. Before we jump into the heavy calculations, here's our quick roadmap for today. We'll be covering the conservation of charge in nodes, mathematical frameworks for KCL, physical verification, step-by-step nodal analysis, and finally, macro systems in the real world.
Okay, let's kick things off with part 1, conservation of charge and nodes.
Listen, the absolute fundamental physical reality governing everything we do in circuit analysis is charge conservation. I really want you to internalize this concept right from the start. In our world of electrical engineering, a node is simply a junction where two or more circuit branches connect. That's it. It's merely a connection point, definitely not a storage device. Meaning, extra charge can't just magically build up there, and it certainly doesn't appear out of thin air. Think of it exactly like a T-junction in a plumbing system. Water can't just pool up inside the pipe joint forever, right? It has to keep flowing. So, looking at this schematic, you can intuitively see that current is really just the net movement of charge flowing predictably through node A and node B. See that main current, the red line? It enters node A, splits into those purple branch currents, and then beautifully recombines over at node B. It's a perfect visual proof of the universal rule of charge conservation. Literally, what goes in absolutely must come out. It's inescapable physics, guys.
Moving right along to Section 2, Mathematical Frameworks for KCL.
Now that we grasp the physical reality, how do we translate this into working math? This comparative table illustrates our two main frameworks. On the left, we've got the equality of sums method. It's super intuitive, honestly perfect for when you're doing manual calculations, because it just says, hey, the sum of currents entering a node exactly equals the sum leaving. Simple enough, right? But on the right, look at the algebraic sum method. This one assigns positive and negative signs based on direction. So maybe entering is positive, leaving is negative, meaning the whole algebraic sum equals exactly 0. This second method, it's a real game changer and absolutely essential for computerized nodal analysis, like when you're using SPICE software to evaluate complex, massive matrices. Next up, Section 3, Physical Verification. Now, as your professor, I'm never going to ask you to just blindly trust some equations on a whiteboard. Let's actually prove this theory in the lab. By comparing real, physical hardware multimeter readings on a breadboard right next to our analytical schematic, we can physically verify our calculations. Check this out. The multimeters are reading 2.7 milliamps and 1.8 milliamps on those individual branches. And when they combine, bam, exactly 4.5 milliamps. Those split currents recombine perfectly, maintaining total analytical symmetry. The math works on paper, and the actual hardware proves it for sure.
Let's roll into Section 4, Step-by-Step Nodal Analysis. Okay, let's take this proven theory and tackle a practical problem using a real, structured, cognitive approach. Just like I show you guys on the chalkboard during our lectures, you should always approach single-node analysis using these 4 simple steps. I promise, this will keep you from getting overwhelmed by complex circuits. Step 1 is the setup. Write out your total current equation. Step 2, the knowns. List out every single variable you already have. Step 3, the unknown. Explicitly identify exactly which branch is missing. And finally, Step 4, the solution. Just use basic algebraic isolation to find your answer. Stick to this flow and circuit analysis becomes a total breeze.
But you might be wondering, what happens when this builds into multiple nodes? Well, when you're facing complex, sequential nodes, we just use a cascading logic technique. It's really elegant. You just apply Kirchhoff's current law to node X first, isolate your variables, and then let that calculated output beautifully carry over as the newly known input for node Y. It's basically a logical domino effect that simplifies even the most intimidating schematic.
And finally, Section 5, Macro Systems in the Real World.
All right, let's step completely out of the textbook for a minute and see how these exact same principles apply to massive real-world engineering systems. You know, a node doesn't have to be just a tiny black dot on a schematic. It can be an entire macro system. Just look at this automotive electrical setup. The entire vehicle itself acts as a single load node. The 8-amp battery supply going in absolutely must perfectly balance the sum of the headlights and taillights coming out. Since we know the headlights pull 5.6 amps, well, simple subtraction tells us exactly what's left over for the taillights. The physics literally scale up flawlessly. Let's make this a bit interactive to really test your intuition with another real-world scenario. Let's say a heavy-duty underground pump is pulling exactly 10 amps on its hot supply line. Based on what we just covered, what exactly must be returning on the neutral line? Think about that strict conservation of charge we've been talking about.
Well, if you guessed exactly 10 amps, you hit the nail right on the head. And why is that? Because Kirchhoff's current law and that universal conservation of charge apply absolutely everywhere. Literally, from microscopic silicon microchips all the way to massive industrial pumps, there are zero leaks in the physics of charge. None.
So as you move forward in your engineering classes and eventually into your actual careers, I want you to always remember one thing. Behind every single intimidating, complex circuit matrix lies this one brilliantly simple, unbreakable rule of the universe. Charge cannot be lost or created at a junction. What goes in absolutely must come out. So with that in mind, how might this powerful, fundamental reality change the way you approach designing your next complex system? Think on that, and I'll catch you in the next explainer.
Welcome back, everyone. Today, we've got a fantastic explainer lined up, focusing on Kirchhoff's current law. We're going to bridge that gap between theoretical physics and real-world engineering. As your professor, my goal today isn't just to throw an equation at you and call it a day. I want to make sure you fundamentally understand how charge actually moves through the incredibly complex circuits you'll be designing in your future careers. But before we get into the heavy math, and we will get into the math, I really want you to ponder this fundamental question. It literally drives everything we're about to cover today. If electrical charge can never be created or destroyed, what exactly happens when it hits a crossroads in a circuit? Just keep that in the back of your mind as we begin. Okay, here is our roadmap for this explainer. 1. The physics of the node. 2. Two mathematical frameworks. 3. Solving single-node unknowns. 4. Cascading multi-node analysis. And 5. Real-world system macronodes. Section 1. The physics of the node. Understanding junctions. Let's dive right in and define exactly what we mean when we talk about a node in electrical circuits. The absolute core principle you need to internalize here: current is really just the net movement of charge over time, meaning what goes in absolutely must come out. I want you to think of a node simply as a junction where branches connect. It's kind of like a roundabout in traffic. It doesn't store charge like a capacitor would. It has zero capacity to hold electrons. It merely directs the traffic. And looking at this visual, it brilliantly illustrates that inevitability. Because extra charge can't physically build up or, magically appear out of thin air, the total current flowing into nodes A and B perfectly equals the current flowing out. Notice how the total source current, IT, splits into 3 parallel branches. But even though the current divides when it recombines at node B, it's the exact same total IT that we started with. The books always balance every single time. Section 2. Two mathematical frameworks, equality versus algebraic sum. Let's see how our intuition translates into a mathematical toolset. So, this table lays out the 2 ways we can express Kirchhoff's current law mathematically. Method 1 is the equality of sums. This simply sets the currents entering equal to the currents leaving. It's super intuitive, and honestly, it's what you'll probably use for manual balancing on your exams. Then we have method 2, the algebraic sum. Here, entering currents get a positive value and leaving currents get a negative value, meaning the whole thing sums to 0. Now, you really need to master the second method, guys, because it's exactly the logic that industry-standard engineering software uses to crunch massive, complex matrices. Now, what's really fascinating here is how the mathematical symmetry perfectly aligns with the physical reality we're measuring with these multimeters. The hardware literally proves the math perfectly. 2.7 milliamps plus 1.8 milliamps recombining at the node will always equal the 4.5 milliamps returning to the source. This isn't just some textbook theory, it is an unbreakable physical law. Section 3. Solving single-node unknowns, isolating variables. Let's roll up our sleeves and apply this logic to solve for some unknown branch currents. I always tell my students to use these 4 simple steps to systematically solve single-node problems without getting lost. Step 1. The setup. Balance that base equation. Step 2. Identify your knowns. Step 3. Isolate your target variable. And Step 4. Calculate the final solution. Seriously, isolate your variables purely in algebra before you plug in any numbers. It'll save you from dropping a negative sign and making a careless error on your finals. Let's test these steps on the schematic we have right here. Step 1, we know total current in equals total current out. Step 2, identifying our knowns.
The total entering current is 100 milliamps, and we can clearly see branches 1 and 3 are pulling 30 and 20 milliamps respectively. Step 3, we isolate our unknown, I2. It's just simple deduction at this point. We take our 100 milliamps entering, subtract the 50 total milliamps leaving through those known branches to find our remainder.
So our missing current must be exactly 50 milliamps to perfectly balance the node. 100 milliamps in, 100 milliamps out. There is absolutely no wiggle room for missing electrons in this equation. Section 4, Cascading Multi-Node Analysis Sequential Logic. Real circuits rarely have just one junction, right? So let's look at how we handle sequential nodes. By first isolating node X on the left, we can calculate the unknown current moving towards node A3. We just take the 5 milliamps entering the system from the source and subtract the 1.5 milliamps dropping down through that first resistor. That leaves us with a remainder of exactly 3.5 milliamps exiting node X straight to the right. Now, the real trick to multi-node analysis is that the calculated output from node X literally carries over to become the known input for node Y. See how that works? We take that 3.5 milliamps, subtract the 1 milliamps dropping down through the next resistor, and boom, we find our final 2.5 milliamp output. Once you solve the flow of one section, it unlocks the next. It's like a giant puzzle. This cascading logic is the absolute foundation for analyzing massive, complex circuit boards. Section 5. Real-world system macronodes beyond the breadboard. For our final section, I want to completely shift your perspective on what constitutes a node. Remember that anything acting as a load in an electrical system is going to have the exact same current supplied to it as leaving it. We call this a macronode. You don't need to know every single tiny wire inside a system to balance it. Actually, you can draw a theoretical black box around an entire skyscraper, treat that massive building as a single junction point, and Kirchhoff's current law still flawlessly applies to the main power lines. Check out this automotive system. We can treat the entire car as one giant macronode. If our battery supplies 8.0 amps of total input, and we know the headlights up front are drawing 5.6 amps, we just deduct that. That tells us we have exactly 2.4 amps remaining for the rear of the car. And since there are two identical taillights, we simply divide that 2.4 in half. We don't even need to measure them directly. The law guarantees that exactly 1.2 amps flow to each taillight. Okay, let's test your intuition with a quick practical engineering check. If an industrial underground pump has 10 amps of current flowing into it on the hot supply line, how much current must be returning on the neutral line? Exactly 10 amps. Because whether it's a microscopic junction on a silicon semiconductor wafer or a massive industrial pump underground, charge conservation applies everywhere. Perfectly. What flows into the load absolutely must return to the source. So I'll leave you with this thought to carry into your next classes. If Kirchhoff's current law perfectly governs the flow of electrons in a microchip and an entire office building, where else does the strict conservation of energy dictate the systems around us? If the universe balances the books so strictly here, what other massive systems are secretly governed by this exact same conservation of flow? Keep looking at the world through this lens, class. Thank you for joining me for this explainer. Study hard, and I will see you next time.